So today on AI Paperslop, we are jumping straight into MAI-Thinking-1, which is subtitled Building a Hill Climbing Machine by the Microsoft AI team.
Yeah, and if you are currently running pre-training clusters, this paper is basically going to rewrite all your rules for scaling.
Oh, absolutely. I mean, let's just get the core metrics on the table right away for everyone. They built a 35 billion active parameter, 1 trillion total parameter mixture of experts model.
Right.
And it scores 52.8% on SW Bench Pro and 97.0% on AIM 2025. And the crazy part is they achieved this entirely from scratch.
Yeah, zero distillation from third-party frontier models.
Right, and a strict ban on synthetic data.
Okay.
So for you as a practitioner, the value here really boils down to 3 radical shifts.
Definitely.
First, they proved that generative evils during pre-training are hopelessly noisy, mandating a return to negative log likelihood. Second, they completely dismantle the rank invariance hypothesis for data mixing at scale.
Which is huge.
It's massive. And third, they introduced this structural initialization trick that prevents MoE routing collapse at step 0.
Right, because we aren't just looking at a model artifact here.
No, exactly.
Yeah.
It's like we're looking at a highly tuned, deterministic hill climbing factory designed to produce better AI rather than just, a single handcrafted sports car.
Yeah, and treating development as this system-level optimization problem, it requires a physical architecture built specifically for rapid iteration.
Right.
So to understand the output, we really have to look at the engine they optimized for their 8K GB200 GPU cluster.
Okay, so let's get into the structural layout.
Right, so structurally, it is a 78-layer, strictly decoder-only network. But they depart from standard transformer layouts by implementing this 5-to-1 ratio of local to global attention.
The memory mechanics of that 5-to-1 split are just highly aggressive. Like for the local attention layers, they enforce a sliding window of 512 tokens using rotary position embedding.
Exactly. So you process the immediate syntactic context locally.
Right. But then for the global attention layer that occurs every 6th block, they just strip out position encoding entirely.
Which is a brilliant maneuver for anyone constantly fighting KV cache limits.
No, for sure.
By dropping positional encoding on the global layers, you aren't forcing the model to memorize the exact absolute distance between 2 tokens that are, say, 80,000 steps apart in the sequence.
Right, because that's just wasted compute.
Exactly. You are allowing the global layer to operate purely on semantic routing. So it identifies that a variable defined in the first paragraph is relevant to a function on page 50 without calculating the exact positional offset.
Which means the compute savings and the KV cache compression during long context inference are massive.
Huge, and they integrate that attention strategy into a very specific MoE configuration.
Right, because we usually see medium sparsity MoE layers applied pretty uniformly.
Yeah, but MAI chose to interleave a high-sparsity MoE layer routing to 8 out of 512 experts with a zero-sparsity, completely dense feed-forward network.
So you get the specialized parameter scaling of the 512 experts, but you anchor it with the dense FFN to maintain representational stability across all the tokens.
Yeah, and that routing stability is where we see one of the most critical engineering interventions in the entire paper.
Oh, the initialization trick.
Yes, because anyone who has trained a sparse MoE from scratch knows the absolute terror of step 0.
Right.
At initialization, your attention softmax is essentially uniform. Every token attends to every other token almost equally.
Which creates this immediate average pooling effect. If every token is pulling in a uniform distribution of all the previous tokens, their vector representations just start to blur together.
Exactly. To the MoE router, a token representing a Python syntax error looks mathematically identical to a token representing a French preposition.
Because it's all just uniform mush.
Right. The router has no distinct features to evaluate, so it just dumps all the tokens into a handful of overloaded experts, and your routing balance completely collapses before the loss curve even starts moving.
Okay, so their fix for this is the zero initialization trick. But wait, so they essentially turn off the defining feature of a transformer, the cross-token detention, at the very beginning of training?
I know, it sounds crazy. They set the RMS norm gains to 0 at initialization. So yes, you are effectively blinding the attention mechanism.
It feels incredibly counterintuitive.
It does, but mathematically, it elegantly prevents those early-stage training spikes. It forces the model to act as a deep stack of isolated feed-forward layers.
Ah, okay. So a token only processes its own local embedding. There's no cross-token contamination yet?
Exactly. By the time the network trains a bit and the RMS norm gains naturally update, the tokens have already developed highly distinct, isolated feature representations.
So when the cross-token attention gradually fades in, the MoE router actually has distinct signatures to look at.
Right. It allows the model to build an internal vocabulary before it attempts syntax.
That makes a lot of sense.
And alongside stabilizing the router, they eliminate another massive source of training noise by abandoning token dropping entirely.
Oh, right, because in standard MoE setups, you set a finite capacity for each expert.
Yeah, and if an expert hits its token limit, any overflow tokens are just dropped. They bypass the MoE layer entirely via a residual connection.
Which creates a subtle causal leakage. Like, if a critical piece of reasoning is contained in a dropped token, the model is forced to guess, which injects noise directly into your gradient updates.
Exactly. So MAI shifted to a fully dropless MoE implementation. They use variable message sizing for their all-to-all communications.
So even if the routing becomes highly imbalanced temporarily, memory usage remains bounded.
Right, because the system dynamically allocates communication blocks based on the active tensor sizes rather than relying on static, hard-coded expert capacities.
So you remove an entire category of noise from the system. But, building a perfectly balanced dropless engine is pointless if your loss curve is lying to you.
Oh, absolutely. And this is where the MAI team had to fundamentally audit their evaluation metrics.
Right. Because if you are running pre-training ablations, the standard industry reflex is to run generative benchmarks like MMLU or math. You want to see if the model is actually getting smarter.
Yeah, but MAI completely rejected that approach for day-to-day ablations. Generative evaluations require autoregressive generation, which is computationally expensive.
And hypersensitive to formatting artifacts.
Exactly. Take the MBPP coding benchmark. The shared prompt structure relies on Unix-style new lines, but the actual problem statements use Windows-style new lines.
Oh, wow. So if you evaluate a mid-training checkpoint, it might possess the underlying logic to solve the coding problem.
But it fails the benchmark simply because its generation halts on a mismatched carriage return.
It is the ultimate false negative. You end up discarding a superior architectural ablation because of a brittle evaluation script.
Right. To bypass this, MAI reverted entirely to negative log likelihood, or NLO. They relied on teacher-forcing metrics applied to held-out, high-quality reference data sets.
So think about your own data pipelines for a second. With NLO, at every prediction step, the model is conditioned on the ground truth prefix. A minor formatting hallucination doesn't compound into a tangent that ruins the entire generation. You are isolating the pure probability distribution.
Right. Are you actually assigning higher probability to the correct next token? It gives you a high signal, low variance metric.
And they formalize this into a metric they call efficiency gain, or EG.
Yeah, EG calculates exactly how much additional compute a baseline model would require to match a new candidate model.
So if an ablation yields an EG of 1.3, the baseline would need 30% more FLOPs to achieve the same NLL.
Right. It provides a ruthless, financially grounded way to measure progress.
And relying on those strict NLL measurements is what led them to accidentally murder the sacred cow of AI scaling the rank invariance hypothesis.
Which is wild. If you are allocating millions of dollars of compute, you generally assume that the relative ordering of data mixtures is preserved as you scale.
Right. If mixture A beats mixture B on a 5 billion parameter model, you stake your cluster on the assumption that mixture A will beat mixture B at 100 billion parameters.
But they proved that assumption is dangerously false. They tested two distinct data recipes on a 5 billion parameter model, a stem-heavy mix and a code-heavy mix.
And at 5B, the stem-heavy mix yielded superior stem NLL scores, right?
Yeah, the concentrated domain knowledge directly improved performance in that specific domain. But when they applied those exact same mixture weights to a 23 billion parameter model, the curves crossed.
Wait, really? The curves actually crossed?
Yeah. The code-heavy mix ultimately outperformed the stem-heavy mix on the stem evaluations at scale.
That is insane. It's like assuming the exact workout routine that makes a great 5K runner will perfectly scale up to train an ultramarathoner. At a certain scale, the actual fuel you need changes entirely.
Exactly. The capacity of a 23 billion parameter model is so vast that it rapidly saturates the unique information contained in the stem-heavy mix.
Because the stem sources were high quality but structurally homogeneous.
Right. The code dataset, on the other hand, possessed vastly more structural diversity, intricate logic branches, nested dependencies, algorithmic edge cases.
So at scale, the diversity of logical structure outscales concentrated domain knowledge.
Yes, the model didn't need more math facts, it needed more complex logical topologies to exercise its parameter count.
Wow. So this breakdown of rank and variance fundamentally changes how you have to construct a pre-training corpus. You cannot blindly trust small-scale ablations for your final data recipe.
No, you really can't.
Which brings us to the actual fuel they fed this architecture. Because data scaling proved so unpredictable, they had to engineer an incredibly precise 30 trillion token diet.
And completely synthetic free.
Yeah, which actively bucks the current industry consensus.
Yeah.
Almost everyone is injecting synthetic AI-generated data into pre-training to boost benchmark performance.
Because the web is essentially tapped out of high-quality human text.
Right, so I have to push back here and ask why MAI would actively handicap themselves when the rest of the industry is relying on synthetic data.
It comes down to the difference between short-term benchmark bumps and long-term robustness. Imitation versus learning.
Okay, unpack that a bit.
Training on synthetic data distilled from frontier models absolutely gives you faster bumps on MMLU. You are imitating the intelligence of a highly polished system.
Right.
But imitation is shallow. The model is copying the surface-level patterns and the tone of the teacher without developing the underlying reasoning engine.
Ah, because you aren't exposing it to the messy human trial and error process.
Exactly. If a model only sees perfectly formatted, synthetically generated Python scripts, it never learns how to recover from a bad variable assignment or a syntax error.
That makes total sense. If the base model's knowledge is a shallow imitation, it lacks the steerability for long RL climbs later on.
Right. The policy doesn't possess the deep, diverse human priors needed to explore complex, unseen solution spaces. It just gets stuck repeating the synthetic formats it memorized.
So they restricted the diet entirely to human data web crawls, GitHub repositories, academic papers.
Yes, but managing 30 trillion tokens of pure human data requires extreme hygiene, particularly deduplication.
Oh, for sure. If you don't control exactly where duplicates exist across your entire corpus, adjusting the weight of one dataset secretly shifts the data from another source.
Right, so MAI utilized a global drop order deduplication strategy. They embedded the entire corpus using Qwen3 embedding to identify semantic duplicates across domains.
Because the graph structure of 30 trillion tokens is incredibly complex. Like, you might have a specific tensor calculus problem living in a public GitHub repository, being debated on a math forum, and cited in an ArcSFS paper.
Exactly. You have to force a hierarchy to maintain your mixture weights.
So MAI established a strict drop order priority. If math forums hold a higher priority in their data recipe, the tensor calculus problem is retained in the form dataset and completely purged from the GitHub and ArcSF datasets.
Right. This guarantees that when they assign a 15% weight to GitHub data, they are actually getting 15% unique GitHub logic, not 15% inflated by overlapping math problems.
And they maintain that rigorous data isolation right through mid-training and context extension.
Yeah, after processing 30 trillion tokens at a 16K context window, they filtered the corpus down to only the highest quality stem and code.
Then they extended the context window to 64K and finally to 256K.
And they monitored the NLL metrics really closely during this phase.
Right, the rapid adaptation finding. When they repacked the data to 256K sequence lengths, the model's NLL dropped to its final optimal plateau within just the first 1 to 10% of the training steps.
The adaptation speed is staggering. It proves that context extension isn't actually a period of active learning.
Because the representational capacity required to leverage long context was already solidified during the initial pre-training phase.
Exactly. The model already understands how to connect concepts across massive distances.
So during that rapid 1 to 10% window, the network is merely calibrating its positional attention parameters to sequence lengths it hasn't physically processed before.
Right. It is unlocking existing potential, not generating new reasoning capacity.
Okay, so you now have a base model with an incredibly pure human vocabulary, an optimized dropless routing engine, and a 256K context window.
But it still doesn't know how to actively reason. It only knows how to predict the next token based on human syntax.
Right. So to teach it how to actually think, you have to put it through the reinforcement learning climb.
And because they explicitly banned synthetic distillation, this model has zero prior exposure to structured reasoning traces.
It has to discover how to build a chain of thought entirely from scratch.
Exactly. And to facilitate this without relying on subjective AI judges, MAI engineered millions of verifiable environments.
Because relying on LLM as a judge introduces subjective bias and hallucinations into your reward signal, right?
Yes, a verifiable environment provides binary mathematical truth. If the model is solving a calculus problem, the output is parsed and evaluated by SIMPy.
Or if it is writing a Python script, the code is dropped into an execution sandbox and run against unit tests. You passed or you failed.
Exactly. There is no partial credit for sounding confident.
And that objective binary reward signal is what prevents the policy from collapsing during thousands of RL steps.
But reinforcement learning is inherently volatile. The policy can easily unlearn its syntax while chasing a reward.
So to anchor the model, they use self-distillation. They take the successful reasoning traces the model generated in previous steps and use them to update the base policy via supervised fine-tuning.
It acts as a ratchet mechanism, locking in successful logic patterns.
But they discovered a hard mathematical limit to this, didn't they?
They did. They identified a self-distillation sweet spot of approximately 1 million reasoning traces.
Wait, only 1 million? What happens if you do more?
If you attempt to distill 2 million or 3 million traces, you actively degrade the model's performance.
It's an issue of overconstraining the policy. When you feed a model too many of its own argmax outputs, the probability distribution of its generations becomes aggressively constrained.
Right, it becomes rigid. It loses the variance and the exploratory capacity required to find novel solutions.
So when you resume the RL phase, the model is too inflexible to navigate around obstacles.
Exactly. The balance between exploitation and exploration is really delicate.
And as the model navigates this RL climb, the researchers documented some fascinating emergent behaviors in its chain of thought traces.
Oh, this is the best part. Without any human prompting, they noticed that weak models guess, while strong models work hard.
I love this because we see this exact progression in human software engineers.
Yeah, so in the early RL checkpoints, when the model faces a complex environment, it immediately attempts to generate the final solution. It just jumps to a solution and fires off a blind guess.
But as the RL process hardens the policy, you see the model physically halt its progression. It begins writing localized exploratory test scripts to confirm the environment dynamics first.
Right. It builds a mental model of the physics before it acts.
And the second observation follows the same trajectory, fixation versus archaeology.
Yes. When tasked with fixing a broken code base, an early-stage, weak model fixates entirely on the mechanics of string editing.
It gets trapped in trial and error, tweaking a single variable, failing the unit test, tweaking it again.
Exactly. But a strong model, refined by the RL climb, acts like an archaeologist.
It's just like a senior dev. A junior dev will just start tweaking code to see if it compiles. But a senior dev spends 90% of the time looking for the source of truth before writing a single line.
Right. The strong model pulls reverted commits, analyzes the repository history, and reads through error logs to deduce why the original architecture was structured that way.
It elevates coding from a string matching exercise to a system-level engineering task. And these behaviors weren't programmed. They weren't imitated from a synthetic data set.
No, they emerged organically from the pressure of verifiable environments acting on a pure human database model.
Which really encapsulates the entire philosophy of the MAI-Thinking-1 paper.
Yeah. The 52.8% on SWE bench isn't the result of a magical new attention mechanism or a secret data source. It is the compounding dividend of ruthless system-level optimizations.
You zero-initialize the attention to stabilize the sparse MoE. You implement variable message sizing for a dropless engine. You enforce strict NLL teacher forcing. You deploy global drop order deduplication. And you subject the architecture to verifiable RL environments.
It is a literal blueprint for building a deterministic hill-climbing machine.
It absolutely is. Huh. But as you look at your own training pipelines this week, I want you to ponder the most disruptive finding we covered.
The rank invariance hypothesis.
Right. The rank invariance hypothesis is dead. If data recipes that fail at 5 billion parameters actually turn out to be the winning strategy at 35 billion parameters, how many brilliant, scalable ideas have AI researchers prematurely abandoned just because they didn't look good on a miniature test model?